Today we have a very interesting topic and very important expert in this field, Dr. Gaike Reel, who's leading IBM Research Quantum Europe. She's an IBM fellow and nanotechnologist, an expert in many fields like molecular electronics and nanoscale semiconductors, who was first interested in physics, as far as I can remember from some previous interviews that I've been watching, and then became attracted to quantum physics as well. So hi, Gaike. We are very, very pleased to meet you, and thank you very much for your time. Yeah, so just to start, a couple of things I'd like to say about what we are about to discuss here is something great, I think, that happened in November. So in November, IBM presented their new quantum processor, Osprey, that run on 233 qubits, and now it's the most powerful quantum computers at the moment, as far as I can understand this. So also the company showed us their roadmap and how quantum computers will solve previously unsolvable problems. So hi, Gaike.
Thank you so much for having me. It's a great pleasure being with you. I really appreciate it.
Thank you very much. So my first question will be, why does the world need quantum computers?
Very good question, right? Quantum computers, they are really a new, completely new, radically different technology than what we are used today. And then the question you ask is, why do we really need them, is of course a very valid question. And then if you look into what we do today with computers, with our classical computers, then you see that there are actually a lot of tasks which are important to us, like weather simulations, simulations of new materials, doing car crash testing without doing it in real, right? Crashing the cars, but really calculating it and understanding without needing to do it experimentally. And so therefore, there are actually many more complex mathematical problems which we would like to solve in this way to accelerate innovation and invention, but it's impossible with the classical computers which we have today, because there are mathematical problems which are so complex then any classical computer cannot solve them today, or even not in the future, even if we make them even bigger. And so therefore we need to come up with something new, how we solve those big problems. And quantum computers have the potential because they are based on quantum physics. And that's really the goal of quantum computers, that we can solve other problems which classical computers cannot solve. And though you can ask, okay, what do you do with those big problems today? Of course, we try to solve them by approximations, by saying, okay, I simplify my problem, and then I see whether I can solve it with a classical computer. And this works to some extent, but it's in many cases not accurate enough, and does not give really the true result you want to have in order to be precise enough to accelerate discoveries. And therefore, quantum computers can have in the future a real impact by being able to solve those big complex problems.
What is this benefit about? You mentioned these supercomputers, like classic ones, which are like these huge machines, and they are high level of performance computers comparing to like my laptop, comparing to those like small computers,
iPads, or whatever. I mean, whatever technology you may want we're using today in our homes, right?
Yeah. And what if we compare them to quantum computers? How are quantum computers better or different to solve those tasks like modeling, as you mentioned before? And why are they better? Why quantum physics are better here?
Yeah. So Yes, we have. Computing has evolved really over the last 70 years, right? The transistor actually is now 75 years back that the transistor was invented. And the transistor is a basic building block. We have built bigger computers. We have built also smaller gadgets because we could make the transistor smaller and can thus improve the microprocessor performance. And on one hand, we could make mobile devices very, very efficient, but also very performing. And on the other hand, we could build very big computers with a lot of power, which we use today for a lot of the calculations, as we mentioned. And today's high-performance computers, they are reaching exascale or have reached exascale performance. And they have tremendous memory, they have tremendous compute power, they have like 27,000 GPUs in one of those computers. They are, football, soccer fields large. But still, some of these problems which we want to precisely calculate in order to do predictions of properties cannot be calculated with them because nature is also very complex. And so these HPC computers, they also actually consume a lot of power, a lot of energy, right? So they may have the top one HPC computer today actually consumes 30 megawatt of power. And that's a lot, right? And still it cannot solve these big problems which we want to solve. And so quantum computers, they are based on the laws of quantum physics. And the laws of quantum physics, they govern also the molecules, the nature, the materials on the nanoscale which is surrounding us. And so I can give you one example in order to perhaps understand a bit the dimension. So if you want to, for example, calculate the properties and the structure of a molecule like caffeine, you may have a cup of coffee right now next to you, then caffeine is a molecule. It's not so big. It has nitrogen, oxygen, hydrogen, and carbon. It has about 100 electrons. And why is it complex to calculate it? Because all these electrons, they interact with each other. And if you would write down the equation and the number of states this equation needs to be solved on a classical computer is 10 to the 48. So it's a number with 48 positions. And this is too big to be solved by any classical computer because the number of atoms would be like a tenth of the Earth. And so quantum computers, however, on the other hand, they are also governed by the laws of quantum mechanics in a similar way as this molecule. So you can, in principle, map your problem on these quantum processors, and they intrinsically have the same, they're governed by the same physics, so that you only need in the range of about 160 qubits in order to solve such a problem. And if I say qubits, and I mean in this case, like ideal qubits, error-corrected qubits.
So what can you already do with this Osprey, the processor that I've already mentioned at the beginning? And can you already model the molecule of caffeine, as you mentioned, or is it like our future? What can you do with it right now? How do you use it right now, this processor?
Yeah. So Osprey, as you mentioned, it has already a very, very high number of qubits. It has actually 433 qubits, and but these are not yet error corrected. And so Osprey right now cannot solve the problem of solving the structure of or the electronic structure of caffeine. But we are building up now really more and more complex processors in order to be able to increase the performance of these processors, right? And the performance of a processor, it's not only the number of qubits, but it's also the quality of the qubit, and it's a speed of how fast you get your result back when you start the computation and how long it takes that you get back the result. And so we have started actually out in 2016 with 5 qubits. Then in 2019, we had 27. And so we increased in last year, or actually 2021, we built the first chip with 127 qubits. And this was the first chip ever which broke the 100 qubit barrier. And so we built up the technology in order to build these big number of qubit chips. On the other hand, we also improved their quality. And then we also actually architect the entire compute architecture where you have the orchestration between the classical computer and the quantum computer to solve in the end these big questions. And so we are now with Osprey and with the chips we're building, we are learning from each generation to the next generation how to improve, how to build these higher number of qubits processors, how to improve the quality of these qubits, and also how to increase the speed. And so if you look at the progress we have made over time, it's a tremendous progress which we have made. But of course, there is still more progress needed. And this is what we actually summarized also on our IBM quantum development roadmap, that where you see the different stages of things which we planned already out, which we have delivered, and the new things which are coming soon.
Mm-hmm. And I know that somewhere there in this roadmap, we have Condor and Flamingo 2023 and 2024, like this year and next year. Which are the perspectives of these processors? And what will those computers be able to do?
Yeah, so it's really so perhaps I give you the picture of the entire technology which we're building up, right? Because you have the qubit, you have the processor which contains many qubits. Then you have the entire hardware stack, the software stack, and then you also have to develop new algorithms in order to solve those problems which we have talked about. And all this development is going on in parallel. So we're working on all these different levels to develop the software, to make it easy also for users to program quantum computers, and then also to increase the complexity of the problems which can be solved. And we built this technology up in really all these different levels. And so important is on one hand that we learn how to build technologically large number of qubits in a processor. And this is, as I mentioned, where we have started is 5, moving to 27, to 65, to 127, last year in November to 433. And then next year we want to demonstrate the Condor chip, which you mentioned. And the Condor chip has more than 1,000 qubits. And to be able to demonstrate this type of computer, you need a lot of technological breakthroughs in order to scale it really up. On the other hand, we also improve the quality of the processor, of the calculation of the qubits. This means, and the coherence time is one part. This I'm now going a bit into detail, but what does it mean at a coherence time? This is actually the time in which you can do these quantum calculations because your qubit is in the quantum state. And the longer, the better. And then you have also how the fidelity of those qubits, so the error rate of those qubits. This should be, of course, very, very low, the error rate. So reducing the errors is something we are working on, and where we also made a lot of progress. That in the end, the performance is improving. And from each generation, we iterate within each generation. So within Osprey, we also improve on the same chip. And also then for Condor, we will then improve also within one generation. And you can then build, solve more complex problems with these chips. So on the other hand, you mentioned also Flamingo, etc., because we have started also at the beginning of this last year, expanded our roadmap to bring in modularity. And so if you look at the roadmap, and unfortunately I don't have a picture with me right now, but there you see that you can build a bigger chip also partition it into smaller chips. And so there are different concepts. So we take, for example, the 133 qubit chip, and we connect several together to build a larger chip. And now it's a question of how you connect these chips. And the first thing you do, you take a classical communication line, which means that you can do quantum calculations within one chip. And then you can, however, classically communicate in parallel with the other one. And with this, you can then also parallelize certain calculations. It's a similar like what you do in an HPC, where you say, I have a problem, I can divide it into different pieces, and I then can run these sub-problems on smaller processors in parallel and get out the result faster or get a better result out. And that's a similar concept which we are now using also for quantum computers, where we say, okay, we have this 133 qubit chip, and we can do then in parallel calculations, and can then make use of this parallelization. The next step is that we not only classically communicate between those processes, but also use quantum communication. And that's an important part because you keep the quantum state even when you exchange information from one part to the other part. And therefore, to the outside user, it looks like a bigger chip, like one bigger quantum chip. And this is really very exciting and very important for scaling to many more qubits than the 1,000 qubit chip, which we want to demonstrate next year. And so this roadmap, we have then different pieces we can play around and bring together. And with this, we want to scale then in the next couple of years to more than 4,000 chips, 4,000 qubits, and continue, of course, to come to a much higher number of qubits also.
Wow, will all these, like these parallel processes and everything you mentioned, help you to build a totally fault-tolerant, or as you say, error-corrected computer? Will you be able to have such kind of computer that will be totally correcting all the errors?
Yeah, those the holy grail of quantum computing is, of course, to build an error-corrected, fault-tolerant quantum computer, because then you can, solve any problem, and it's a universal machine then. And this is a path where we are on, right? So we have selected a technology which we can build towards that holy grail goal. But the important part is in between, because there is not only the error correction, but there is also error suppression or error mitigation, which you can utilize in order to get quantum advantage earlier. This means, and so perhaps I can specify quantum advantage, it means really that you, by using a quantum computer for a certain problem, you can get the result faster, or you can get a more accurate result, or you can get the result at higher energy efficiency, which classical computers cannot do. So that's the, this is kind of how we define quantum advantage. And the next step for us is really demonstrating also this quantum advantage, because this also means, then, of course, that you showed that, for an example, that quantum computers provide this advantage compared and show their potential in reality. And that's what we are working on. This is why we improve on all these stacks. I'm excited also very much about new algorithms which are developed, which show that we can cut bigger problems into smaller problems, solve them on these quantum processors which we have them today, and then stitch them back together. We are improving on the quality of the qubits, and thus we are really working towards the quantum advantage. And what I mentioned before, the error suppression and error mitigation is something which we have started to use. And I can give you a bit simplified example of it, which means if today errors appear in these quantum bits, right? But if you understand your error, And for example, you intentionally increase your error, and then you watch the effect on the result, and you do this a couple of times, then you can actually refer back to what it means if you would have 0 error. And this actually is one approach to get a more accurate result. And this comes with some overhead, but we are soon at a stage that you can use these error suppression and mitigation techniques to reach the quantum advantage. That's really one of the next goals.
While you were answering to this question, we received in our chat a question from Victor. I think this is like almost the same that you just have said. Could you tell more about different ways of dealing with errors, correction, mitigation? If there's something you'd like to add here, we can discuss Victor's question right now.
Yeah, so mitigation is in principle what I just explained, right? That you better understand the error, you intentionally also increase your error in steps, and then you kind of go back and say, okay, what would it mean then if I would have 0 error? What would the result be? You can actually see that out of your data. That's one way. It's called error mitigation. And then error correction means really that you measure the error and then you correct exactly for that error. And this has this means that you need more qubits in order to build such a error corrected qubit, because in the quantum physics you cannot without destroying the quantum information measure your qubit. So you need a different approach to understand what your error is and then correct for it. And this means you need many more qubits than one in order to correct. And in order to reach that, you also need to have a certain quality already achieved by your qubits. And that's a range of 10 to the minus 4. And that's something what we are at the border to reach. And then you can make the demonstration or use error correction in your chip. So scaling the number of qubits, improving the quality of your qubits, and then you can start to use error correction. But we do not have to wait that we have error correction until we demonstrate that we want to demonstrate quantum advantage.
What about Kookaburra, if I pronounce it right? It will have, as far as I can remember, more than 4,000 qubits,
yeah, that's right.
If I'm not wrong. How will this processor deal with errors?
So again, it's a bit the same, right? We have more qubits. We have used also the modularity approach, and we also reduce, and we want to reduce the individual error of a qubit, like the fidelity, and having this and at the beyond a certain number, then we can start implementing error correction and can test it. And I think the question, there are other types of errors you have to deal with. Yes, there are more errors. There could be crosstalk between different qubits, right? There could be also errors which are due to charge, which you have sitting somewhere. And this can lead to like two-level jumps. There could be also actually some cosmic rays which could hit your chip and may create an error. So there are many different types of error. When you talk to these qubits, the ones which we are using, these are actually superconducting qubits. And these superconducting qubits you talk to by microwave pulses. So if you want to talk to your qubit, you have to give some microwave pulses. And then you can control and measure your qubits. And these microwave pulses, they have to be very correct. So if you have some error also in providing these microwave pulses, this can also come from noise in your electronics or other things, then this may give a wrong reading or may give a wrong pulse to your qubit and such control it in the wrong way, right? Or has an error on the qubit. So there are many different ways where errors can come from, and you need to work and optimize all these different fronts.
Okay, thank you very much. We have another questions from Victor. I think we'll go back to them and talk about errors somewhere closer to the end. I have also some probably like a little bit silly question, because we're not all of us are engineers here. And this question is the logic of writing algorithms to classic computers are, I guess, not same, but at least similar as to quantum computers?
So do I understand right? You asking how you develop algorithms, or what is different in an algorithm compared to a classical one? Yeah. Mm-hmm. Yes. I mean, I've mentioned a bit that, of course, the quantum computers are governed by the laws of quantum physics. And quantum physics has these strange phenomena like superposition, inference, and also entanglement, and which is a correlation between these two qubits. And these three things together is actually what you want to utilize for your quantum algorithm, because this is the power, the superpower which quantum computer bring compared to classical computer. So therefore, in an algorithm, you have to use these three quantum phenomena in the best way to provide or to achieve an advantage by the quantum computer. So it's really a different thinking and writing of algorithm, because you have to utilize these three effects.
So an engineer who's now using a classic code should also know quantum physics to be able to work with quantum computers, as far as I can understand, right?
So actually, if you know Python, then you can also program a quantum computer, because we are abstracting a lot already how to compute, right? And so when you look at our software stack right now, then you have, of course, you have at the very bottom, you have the hardware. Then you have to talk the hardware. I mentioned that you have to provide microwave pulses to the hardware. So you have to have a software which translate your algorithm or your basic functions into these pulses. Then this is kind of the kernel developer, how we call it, right? And the kernel developer, she or he has to understand really a bit of how the quantum computer works in order to make this translation of the operation to your quantum computer. Then you have the next level of developer, the algorithm developer, and here you really want to imply also these, what I mentioned before, understand, to use these entanglement, etc. And then these algorithm developers, however, they prepare then primitives you can use also as a model developer. And as a model developer, you need to know not so much about how a quantum computer works, because you can use the tools which are developed by the algorithm developer in order to solve your problem. So that's the logic of our stack, right? And so if you, for example, then you want to solve a certain problem, you want to use that algorithm, and then it's in principle implemented, and you just need to know the corresponding Python in order to then solve the problem. We also actually do a lot on the education and training side, where we also provide a Qiskit open textbook. So if you want to learn about Qiskit is an open source language which you can use to program a quantum computer. And I think there are many programs which we have from summer schools or hackathons, or we also support universities and applied universities to teach it. Also, there's really a lot of information available, videos, recordings also on YouTube you can watch in order to learn. And there are also like Jupyter notebooks which you can use and apply to your problem and test and learn.
Wow, this is very interesting. Thank you. Also, now artificial intelligence is something that is already in our culture. So my question will be, what will we do? What can we do? What will quantum computer be able to do with artificial intelligence?
Yes, of course, artificial intelligence is something which is already around for a long time, right? It has been developed in the 50s already. There was the first algorithms, but the compute power was not high enough. But today we have improved on the classical compute power a lot, that you can already do very, very useful artificial intelligence. And in quantum computers, there, from the algorithm side, there is also quite some interest in doing machine learning and doing quantum machine learning, so making use of the specialness of quantum also for machine learning. And one interesting problem in that space is actually the classification problem. You want to classify like blue dots and yellow dots, right? I want to separate. And you need feature space for that. And actually, if you use a quantum feature space, then you can achieve a much higher accuracy, because you can make use also of entanglement. And this has been actually theoretically proven, and also practically on a small examples, on small model examples shown, that with increasing the entanglement, you can improve the classification of machine learning problems with quantum computers. That's one example.
Mm-hmm. Thank you. And okay, this is it's already something that remind me of like science fiction. And I remember one of your interviews, you said that quantum computers are no longer the topic of science fiction, as they are real right now. But I've noticed that they do remain the topic in sci-fi as well, somehow influencing on how people imagine these technologies through the way it is represented in mass culture. And one of the examples that comes to my mind are TV series devs. I don't know if you've heard of him, but there was this idea that, as far as I can remember, that in a deterministic and computable universe, we can build a quantum computer that is able to model past and future in almost like details. Does this idea sound sci-fi-like or true-like, like probable to you?
That's a very interesting question. I think it depends a bit on which future you mean, right? If you look, for example, into weather modeling, and you want to predict the future of how the weather will change, then of course with more compute power, you can do a better job in modeling the future. So it really depends on which type of future you mean, whether it's really sci-fi or whether I think, yeah, that's real, and we are working on that. So because what we want to do is, of course, by using quantum computers, have more compute power for predicting certain things, for calculating scenarios, which are bigger than we can do today, for also understanding of how certain things. For example, if you look at at medicine, right, there are finding cures for certain diseases is very difficult, because a disease is at each person different. And so you need to do like more go towards personal medicine, which is discussed already also for a long time, but it's very difficult to fully understand your body or do protein folding as a first step and things like that. And so there are lots of complex questions. So I think there's a lot of potential for the future, what can be done with more compute power. Because if you think back in the 70s, and I know all of you will be much younger, but in the 70s, when the computing, the classical computing, where processors were built, which were small, of course, much smaller than today, right? And this era started where we built classical microprocessors no one would have had imagined what we can do with these things today. But today we have mobile phones, we have watches which can, where we can phone with and can do even complex calculations on. But we couldn't predict that at that time. And I feel a bit the same today with quantum computers, that today we cannot really predict what we will be able to do in the future with them.
Are there any like risks to be afraid of what quantum computer will be able to do, or what do you think? When we speak about AI, there are many things that we have to probably be afraid of. What about quantum computers?
So quantum computers, there is of course also some risks involved, right? And I think the one risk which is often discussed today is that there is a so-called Shor algorithm many of you may have heard of, which has been developed, I think, in 1994 already. So theoretically proven that with a Shor algorithm, you can identify the prime numbers very easily, even of very big numbers. And this is the method. So finding the prime numbers is a method of where all our cryptography is based on. And a quantum computer can do this instead of 300 years in 30 seconds for big numbers. And this means, of course, if the current cryptography which we use is then, if such a big quantum computer, which is error corrected and big enough, is around, then one can decipher and decrypt the data which we store today. And that's a risk which we have recognized, of course, very, very early, and have started to work then right away on new encryption methods, which cannot be solved by quantum computers fast. And so this work has been going on for quite some time. It's also an international effort where the National Institute of Standards has launched a couple of years back, like a competition to find a new encryption way, which is quantum safe. And last year in August, after many kind of rounds of selection and testing of those new algorithms for encryption, which is so-called quantum safe encryption methods, there has been 4 chosen, which are now to become a standard. And so we are implementing, and we have implemented those standards already on some of our storage products, so that we can make already today sure that the data which is generated today, or which we have today, can be then stored with these new encryption methods, which are safe, and which can then, if a quantum computer, which is error corrected, which has a high enough number of qubits, cannot be broken.
Mm-hmm. Thank you. I remember Leonid told me that you have an expert in cryptography and safety and everything you just mentioned with Ukrainian roots. So I think we would really love to meet him as well one day. And thank you that you answered all of those questions. One last question from me, and then we'll go to everyone else's questions. So this one from me is, do you remember the moment when you became so attracted to quantum physics? I remember watching your previous interviews or your lectures at conferences, and I saw that you are very, very into it. You really love what you do. It's obviously from how you talk about it. And do you remember the moment when it all started?
So actually, I have a passion for mathematics and actually for mathematics for a long time. And for me, a big moment was to realize that actually what I love to do is applying math to solve problems, and also use my hands to experiment. So that's why I became actually a physicist. And then when I studied physics, and physics is how to say it? In physics, you learn to logically think, and you also increase your frustration tolerance. But then if you have worked hard on the topic and you found the solution or you understand what's behind, then this is so fascinating and it gives you really a satisfactory feeling, right? And when I studied alone in quantum physics at the university, it was pretty similar. It was at the very beginning very frustrating because I didn't understand it. And so then you kind of, you try hard and you read about it and you make connections, you learn more, you link different dots you have. And then if you understand the concept behind, and actually it's if you understand the mass, and the concept is also much easier to kind of understand and grasp. And then if you see this also in reality in the lab that it works, I mean, this is just unbelievably fascinating.
Wow, thank you very much. Just for all of us who are here, I would like to remind you that you can ask a question by using your voice, not only texting. So you can turn on your microphone and you can ask whatever you'd like to ask. And while you're thinking, I'm going to read the question that we haven't answered before. It was about the errors again, that they are not only decoherence. What are there other type of errors you have to deal with? If you have something to add here to this question, then we would like to hear.
Yeah. I think I tried to answer it before already, that there are many more errors which can appear. They can come from the electronics to shape the microwave pulses which are needed to talk to the qubits. They can come from charges which may be around and lead to changes. They can be coming from the design and some crosstalk. There are many types of things which can happen. And it's a way of, this has been optimized already for quite some while, but there are many more things what can be done. And this is what we're working on as a team. Thank you.
And there's another question from Mikola that he already asked here in our chat. He cannot use his voice because I know that is in an island place right now, so he doesn't want to interrupt everybody. So he asked, Osprey has already high number of qubits, but limited number of operation due to errors. Does it already allow for a quantum advantage on some classes of problems? What would those problems be? NVIDIA used tensor networks to simulate hundreds of qubits on classical GPU-based supercomputers. Is there a class of problems on which Osprey can perform better than those simulators?
Yeah, so very good question. Thank you very much. So the question about the simulation, for example, so a quantum computer, a classical computer, also not a GPU, cannot simulate a processor, which is a quantum processor with more than 100 qubits. And so the even already the Eagle could not be calculated or modeled, simulated by a classical computer because of the number of states you can generate with it, right? And so also Osprey cannot be simulated. So we learn actually a lot by having these real quantum processors because they cannot be simulated. And then your first question is about whether we have a higher number of qubits, but limited is the number of operation. So as you correctly point out, you have on one hand the number of qubits, which is important, and on the other hand, also the number of gate operations you can apply before your error or before an error masks the result. And this we call actually the depth. So the number of qubits we call the widths, and what you refer to as we call the depths. And this is something which depends on the fidelity, on the error rate. So this is why we are improving constantly and continuously the error rate within our processors and in our systems. One part is also the coherence time, which is important, the fidelity, which I mentioned. And so one of the challenges we have, and a challenge actually not we have, a challenge we set out for the crowd is, because next year we want to build a system, a quantum system, with a depth of 100 and a width of 100. And the challenge is to come up with a problem which can provide then quantum advantage with this 100 times 100 width and depth. And this is currently where, you know, a lot of researchers are working on to come up with the right problem and with the right way of solving it, the right algorithm that you can provide quantum advantage with this 100 times 100. So a width of 100 and a depth of 100.
Thank you very much. Does anybody else have some questions? You can, just reminding you, turn on your microphone and ask, or write in the chat. I think we have a couple of minutes, if you don't mind, Heike. So do you have something to ask here, to add here? Except we are all thankful very much for joining our Kуншткамера here. And I see that you probably asked everything that you were interested in. I hope, yeah. Victor?
I think I have one more small question. As I know, to perceive the quantum state, it is common practice to use multiple physical qubits to represent one qubit which will be available to the algorithm. So in your next generation Osprey computer, you said it will contain 4,000 qubits. It sounds like a lot. And are those physical qubits or actual qubits which will be available to the algorithm?
Yeah, so so on the Kуншткамера, we want to demonstrate like 4,158 qubits. And these are not yet logical qubits, but these are, you know, the physical qubits. But of course, what we do in parallel is also, as I mentioned, improve the quality of the qubits. And also we have the modularity as part of it, that we can also, for example, use them in different ways. This means use algorithmic tricks also, which are so-called circuit knitting and circuit cutting, in order to solve bigger problems, but use an algorithm to actually cut down them in smaller problems and solve them on this chip with more than 4,000 qubits.
And all these 4,000 qubits are placed on one chip or on the smaller cores, which are interconnected via classical links?
Yeah, so that's exactly where we want to use a modular concept, which I explained before, where we have different ways of how we can connect the sub-modules. And these sub-modules, which is now the smaller processor, right? And they can be connected classically or also by quantum links. And that's very important, because if you connect them by quantum links, then they can also exchange quantum information, and they appear to you as a user as one big chip.
Yes, because as I understand, some algorithms just require whole memory available, all the bits it can get, and if you divide into smaller numbers, it comes more like a classical computer with a bit of acceleration. And
yeah, so in the first pass, which we actually want to demonstrate this year, where we call this Heron, which is actually these are 133 qubit chips, but multiple of them. And they are connected this year by classical communication, because we are just starting to implement this modular concept. And when they are classically connected, then you can actually do multi-threading, which means that you can solve, for example, the same problem in parallel on many things, and you can do statistics. Or you can also use it for certain algorithmic changes like dynamic circuits, etc., where you can communicate between these chips within your coherence time and thus can also make use of some of the algorithmic advantages.
Lot to think about. Thank you for answer.
Thank you very much. And also there's a question from Leo. He said maybe Heike can comment on how quantum computers could become useful, reach quantum advantage, even before we have built a fully quantum error-connected or fault-tolerant quantum computer.
Yeah, of course. I mean, the fault tolerancy and the fully corrected, that's really the holy grail, of course. But this does not mean that we cannot achieve quantum advantage before. And there is actually a regime which we are targeting where you can use this error suppression or error mitigation, which I mentioned before, where you can then reach already quantum advantage without really having a fully error corrected. And so what does it mean? It means that you need to come to a regime where you the overhead which you need. For example, I mentioned before, when you do error mitigation, then you have a certain error, you know it, then you increase the error intentionally a bit, you increase it a bit further, and then you can actually estimate of what would it be if you would have zero error, and this increases your result. But you see already you need to do a couple of more measurements in order to do this estimation. And this means the overhead, right? And so you can get with a certain quality of your qubits in a regime where you have less overhead compared to a classical simulation and achieve quantum advantage. And this is a regime which we are targeting as a next step, right? And I think this 100 times 100 challenge is very, very exciting because you have then also a high at 100 widths, 100 depths, and now you can map a problem on this. And this is really the challenge of what people are working on right now, is to figure out what type of problem, which is very hard to solve classically, can be used to map on this compute capability which will be provided next year and provide an advantage.
We are very interested, I think, and looking forward to see the next steps and to see the progress of all the technology. I think it's very, very interesting, and it's really fascinating that we already not only think about it and talk about it, but can already see some results of it. Thank you very much. I think that we all kind of asked everything we wanted to ask, and also I see that I remember Leo told us that an hour will be like the best time for us, and I see this hour is already passing. So I want to thank you very much. It was Dr. Heike Rіль, who's leading IBM Research Quantum Europe and who's an IBM fellow. Thank you very much. And if you have like something to add to the end of our conversation here, we would like to hear whatever you want to say to us. Thank you very much.
Yes, thank you. So I wanted to highlight that there is really a lot of opportunities because quantum is at an early stage, but it's a fast, a really fast developing area. There's a lot of things which can be learned. There's lots of material also online available. I mentioned the Qiskit open textbook, which is openly available. And there are also videos and other things where people can start into getting into quantum, getting excited about it and learning, because I think it will be with us for a long time, and it's good to start early to learn it and figure out how to apply it. So I thank you very much for having me, for your great questions, and I truly wish you all the very best. Thank you very much.